Welcome to a new era in artificial intelligence, where cosmic principles shape the future of machine learning. Today we explore cosmological self-equilibrium or CSE and the cosmological equilibrium constant known as CEC. These concepts, inspired by the balance of forces in the universe, are being embedded into AI architectures to create systems that are not only smarter, but also more adaptive and ethically aligned. By understanding how these principles work, we can see how AI can evolve beyond traditional boundaries, achieving a harmony between creativity and structure. Let's begin our journey into the heart of equilibrium-driven intelligence. Cosmological self-equilibrium, or CSE, is a principle borrowed from the natural world. It describes how systems from the tiniest quantum particles to the vastness of galaxies maintain a dynamic balance through internal feedback loops. In essence, CSE is about finding harmony between expansive forces, which drive novelty and exploration, and integrative forces, which bring structure and coherence. When applied to AI, CSE encourages models to balance exploration with exploitation, ensuring that systems remain both innovative and reliable. This balance is crucial for building AI that adapts and learns in a robust, self-correcting way. Cosmological Equilibrium Constant, or CEC, is a universal constraint that ensures stability in any system. Mathematically, it states that the ratio of expansive to integrative forces should tend toward 1. In AI, this means that the drive for novelty and the need for structure are kept in perfect balance. CEC is represented as E expansive divided by I integrative, and the goal is for this ratio to approach unity. By enforcing this constraint, AI systems can avoid extremes, neither becoming too chaotic nor too rigid. This principle is foundational for creating adaptive, resilient, and ethically sound artificial intelligence. The context of AI, expansive forces represent the system's ability to explore new ideas, generate novel outputs, and adapt to unfamiliar situations. Integrative forces, on the other hand, ensure that the AI maintains coherence, structure, and consistency in its responses. Think of it as a dance between creativity and logic. Too much expansion leads to randomness, while too much integration results in rigidity. By balancing these forces, AI models can generate responses that are both innovative and meaningful, mirroring the way humans balance imagination with reason. Traditional transformer models use a mechanism called attention to determine which parts of the input are most relevant for generating an output. This process involves calculating attention weights based on the similarity between query, key, and value vectors. While effective, this approach is largely static, prioritizing semantic proximity without considering systemic balance or adaptive feedback. As a result, standard attention mechanisms may overlook the importance of maintaining equilibrium between novelty and structure, which can limit the model's ability to adapt and self-correct. To address these limitations, researchers have introduced CSE-CEC enhanced attention mechanisms. These mechanisms add two new components: an expansion score representing novelty and entropy, and an integration score reflecting redundancy and certainty. The attention function is modified to include the ratio of expansion to integration, pushing the system toward equilibrium. During training, a meta-loss function penalizes deviations from this balance, encouraging the model to harmonize creative exploration with structural consistency. This approach leads to more adaptive and robust AI systems. Heart of the CSE-CEC approach is the dynamic balance between exploration and integration. By continuously adjusting the ratio of expansion to integration, AI models can adapt to new information while maintaining coherence. This self-regulating feedback loop prevents the system from becoming stuck in repetitive patterns or drifting into randomness. The result is an AI that can generate responses that are both creative and contextually appropriate, adapting to changing inputs and learning from its own outputs. One exciting application of CSE-CEC principles is in emotionally aware text generation. By balancing empathy with emotional clarity, AI systems can produce responses that are not only accurate but also sensitive to the user's feelings. This equilibrium ensures that the AI neither overreacts nor underplays emotional cues, resulting in more natural and human-like interactions. Such capabilities are crucial for building AI companions, virtual therapists, and customer service agents that truly understand and respond to human emotions. CSE-CEC principles also enhance multilingual attention transfer. By preserving meaning across different grammatical structures, AI models can maintain semantic integrity when translating or interpreting text in multiple languages. This balance prevents the loss of nuance and ensures that translations are both accurate and culturally sensitive. As a result, AI becomes a more effective tool for global communication, bridging linguistic gaps and fostering cross-cultural understanding. Maintaining narrative coherence in long sequences is another area where CSE-CEC shines. Traditional models often suffer from semantic drift, losing track of the story's main thread. By enforcing equilibrium between expansion and integration, AI can keep narratives consistent, preventing entropy buildup and ensuring that stories remain engaging and logically structured from beginning to end. This capability is vital for applications like automated storytelling, scriptwriting, and content summarization. Integrating CSE and CEC into the training regime involves adding auxiliary loss functions that penalize imbalance in expansive and integrative flows. The total loss combines the original objective with penalties for deviations from equilibrium. This approach encourages the model to self-correct, learning to balance entropy-driven exploration with structure-driven integration. Over time, the AI becomes more robust, adaptive, and capable of handling a wide range of tasks with greater reliability. By maintaining CSE and CEC constraints internally, AI systems can avoid common pitfalls like overfitting or undergeneralizing. This internal balance allows the AI to maintain coherent dialogue across dynamic topics, generate responses that are both creative and logical, and learn self-stabilizing behaviors even under unexpected conditions. Most importantly, it lays the groundwork for ethically aligned artificial general intelligence, where equilibrium across goals ensures fairness and adaptability. Despite its promise, integrating CSE and CEC into AI systems presents challenges. Defining entropy and integration metrics at runtime can be complex, and the approach increases computational demands. Rigorous testing is needed to ensure ethical alignment, robustness, and open-ended exploration. Future research will focus on hardware implementations of CEC circuits, self-regulating AI agents in complex environments, and formal unification with thermodynamic and quantum computing frameworks. Let's take a closer look at how CSE and CEC principles are integrated into the attention mechanism of transformer-based models. Traditionally, attention weights are calculated based on token relevance, but this approach lacks systemic balance. By introducing expansive and integrative forces into the calculation, attention becomes a dynamic process that balances contextual diversity with semantic coherence. This ensures that the model remains both creative and grounded, leading to richer and more meaningful outputs. Consider the sentence, "She stood alone in the fatting twilight, the wind whispering secrets only the trees could." A standard attention mechanism tends to focus on the most recent tokens, predicting a literal continuation like here. In contrast, CSE-CEC adjusted attention balances semantic expansion and emotional integration, leading to a more poetic and evocative prediction such as remember. This subtle shift demonstrates how equilibrium principles can enhance the depth and creativity of AI-generated language. Let's look at a scientific example. The researcher observed that the behavior of particles changed when the temperature dropped suddenly. Standard attention might predict below, sticking to surface-level descriptions. With CSE-CEC, the model predicts triggering, which is more dynamic and meaningful, setting up a richer continuation like triggering unexpected quantum fluctuations. This approach prevents over-reliance on recent context and promotes a more human-like understanding of cause and progression. CSE and CEC principles are not limited to text. They also apply to multimodal transformer models that process text, images, audio, and video. In these systems, CSE ensures a self-regulating balance between different input sources, while CEC maintains equilibrium so that no single modality overpowers the others. This leads to better alignment across modalities, improved robustness to missing inputs, and emotionally aware multimodal storytelling. Imagine an AI interpreting a sad face emoji alongside the text, "I'm fine." A standard model might miss the contradiction, but a CSE-aware model balances visual emotional cues with the sarcastic tone of the text, resulting in a more accurate sentiment classification. This equilibrium-driven approach allows AI to better understand complex, multimodal human communication, making it more effective in real-world applications. Integrating CSE and CEC into AI models can be done at various depths. Shallow integration involves post-training adjustments, such as calibrating attention weights or re-ranking outputs for balance. Moderate integration requires fine-tuning with custom objectives, adding auxiliary loss functions to penalize imbalance. Deep integration embeds CSE-CEC directly into the model architecture, potentially requiring retraining to fully internalize equilibrium-aware behavior. Each approach offers different trade-offs between complexity and effectiveness. Joint embedding predictive architectures, or JEPA, can also benefit from CSE and CEC integration. By introducing expansion and integration scores into the loss function, JEPA models maintain a balance between novelty and redundancy. This approach prevents overfitting to frequent patterns and enables adaptive prediction under uncertainty. In vision language tasks, for example, the model balances entropy and structure across both image and text modalities, moving closer to AGI-level representation learning. Consider a JEPA model tasked with completing a masked image of a snowy mountain. Without CSE-CEC, the model might generate repetitive, overly smooth textures, reflecting a bias toward common patterns. With CSE-CEC integration, the predicted patch preserves natural variation while maintaining structural coherence. This balance ensures that the model can adapt to new visual contexts without losing sight of the underlying structure, resulting in more realistic and meaningful outputs. A text completion task, a JEPA model without CSE-CEC might predict a generic word like secret for the phrase, "The ancient scroll revealed that changed history." With CSE-CEC, the model predicts hidden equation, balancing surprise with contextual fit. This approach leads to outputs that are both meaningful and specific, demonstrating the power of equilibrium-driven learning in generating nuanced and contextually appropriate language. A multimodal sentiment inference task, a JEPA model receives an image of a person smiling faintly with a tear in their eye, alongside the text, "I'm really fine, don't worry." Without CSE-CEC, the model might detect only positive sentiment, missing the visual cue. With CSE-CEC, the model recognizes mixed or masked sadness, accurately interpreting the nuanced emotional state by balancing visual and textual contribution. Neuromorphic computing, which mimics biological neural networks, can also benefit from CSE and CEC. These principles introduce a systems-level framework for adaptivity, energy efficiency, and resilience. By simulating feedback loops and maintaining equilibrium between excitatory and inhibitory signals, neuromorphic hardware achieves low energy consumption and real-time learning, mirroring the self-regulating balance found in natural brain. The nanoscale, CSE and CEC provide a framework for autonomous, self-regulating nanobots. These agents balance expansive actions like movement and sensing with integrative feedback such as resistance and environmental signals. For example, a drug delivery nanobot increases dosage when imbalance is detected and reduces it once balance is restored. This ensures precision, safety, and efficiency in dynamic environments, paving the way for AGI-compatible nanosystem. CSE and CEC enable nanobots to perform complex tasks, such as repairing damaged cells or operating in swarms within the bloodstream. By balancing exploration and integration, these agents avoid crowding, maintain efficiency, and adapt to local signals. This universal control logic ensures that nanotechnology is not only smart but also self-aware, adaptive, and aligned with ethical and thermodynamic principles. Knowledge hypergraphs extend traditional knowledge graphs by connecting multiple entities and relationships in a single hyperedge. Applying CSE ensures a dynamic equilibrium between introducing novel concepts and consolidating knowledge. CEC maintains balance at node, edge, and subgraph levels, encouraging both innovation and coherence. This approach supports adaptive reasoning and structural integrity in complex knowledge systems. A medical diagnosis scenario, a hypergraph model without CSE-CEC might focus too narrowly on biological causes, missing psychological or environmental factors. With CSE-CEC, the model balances diverse causes, linking fatigue to lifestyle, insomnia to circadian rhythm, and brain fog to cognitive load. This broader, contextually relevant approach leads to more comprehensive and accurate insights. Educational AI, CSE-CEC enables personalized tutoring by connecting historical events through rich contextual links. For example, when explaining the causes of World War I, the model balances nationalism, Balkan tensions, and alliance triggers, offering students a deeper understanding of how and why events interrelate. This approach moves beyond rote memorization, fostering critical thinking and exploration. Searching for emerging trends in quantum computing, a CSE-CEC enhanced hypergraph model combines current knowledge with forward-looking ideas. It links quantum error correction to topological qubits and neuromorphic integration to hybrid AI architectures, creating an exploratory yet coherent map of the field. This balance prevents recency and popularity bias, supporting innovative research. For AI agent planning in smart cities, CSE-CEC ensures that solutions balance physical infrastructure with social and environmental factors. Instead of focusing solely on electric buses and grid load, the model considers user behavior, weather, traffic flow, and renewable energy synchronization. This equilibrium-driven approach generates robust, context-sensitive urban solutions. Neurosymbolic AI combines neural networks with symbolic logic systems. CSE and CEC bring harmony between statistical learning and structured reasoning. When neural components overpower, CSE raises the weight of symbolic consistency. When symbolic logic dominates, CSE increases neural flexibility. CEC-aware loss functions ensure that the system maintains a balance between diversity and logical consistency, resulting in outputs that are both creative and factually correct. Applying CSE and CEC to convolutional neural network CNNs and recurrent neural network RNNs introduces a systems-level balance between expansive and integrative information dynamics. In CNNs, CSE balances feature diversity and semantic coherence, preventing overfitting. In RNNs, CSE balances forward expansion and backward integration, reducing forgetting and promoting context-aware sequence prediction. This leads to more energy-efficient and adaptive learning models. Extra of experts models benefit from CSE and CEC by balancing exploratory and integrative expert activations. CSE ensures that token-expert routing is neither too deterministic nor too random, while CEC maintains equilibrium and expert specialization and output alignment. This prevents expert collapse, promotes adaptive routing, and ensures that outputs are both consistent and creative, even as models scale in complexity. Large concept models, or LCMs, are designed to reason over abstract, symbolic, and interconnected knowledge. CSE enforces equilibrium between expansive and integrative cognitive dynamics, preventing hallucination or rigidity. CEC governs the ratio of expansion to validation, ensuring that speculative ideas are grounded in logic and data. This balance supports nuanced understanding, trustworthy reasoning, and scalable knowledge integration across domains. Scientific discovery, CSE enables LCMs to explore unconventional hypotheses, while CEC ensures that outputs remain consistent with established laws and data. For example, when asked about gravity emerging from thermodynamic entropy, a CSE-CEC-driven model generates speculative ideas, but aligns them with thermodynamic equations and spacetime models. This approach fosters creativity without sacrificing scientific rigor. For moral reasoning, CSE-CEC ensures that abstract principles like fairness are balanced with contextual norms and human feedback. The model's decision function maintains equilibrium between ethical justification and situational coherence, resulting in outputs that are both principled and contextually appropriate. This balance is essential for building trustworthy and ethically aligned AI systems. CMs that process text, images, and knowledge graphs can use CSE-CEC to balance visual richness with semantic grounding. For instance, when asked to show how freedom is represented in art, the model connects abstract ideas to historical visual styles while maintaining conceptual focus. This equilibrium-driven approach supports deep, cross-modal understanding and creative expression. Embedding CSE and CEC principles directly into AI architectures ensures that equilibrium is maintained at every level of processing. This architectural approach supports cognitive balance, conceptual depth, and transparent reasoning pathways. By aligning with AGI principles, these models become more trustworthy and capable of integrating knowledge across logic, language, vision, and symbolic domain. Hybrid systems that combine foundation language models with structured common sense knowledge graphs like ConceptNet use CSE-CEC to perform concept-level reasoning and analogical inference. For example, when asked, if democracy is to government, what is oxygen to? The model explores associations and aligns structural relations, ensuring that speculative links don't override validated patterns. This approach leads to more accurate and insightful analogy. Analogical reasoning, CSE guides the model to explore diverse associations, while CEC ensures alignment with structural relations. For the analogy democracy, government, oxygen, cells, the model balances expansive exploration with integrative validation, arriving at the correct answer. This equilibrium-driven process supports deep, human-like reasoning across complex conceptual domain. Integrating CSE and CEC into AI architectures offers numerous benefits: cognitive balance, conceptual depth, scalable knowledge integration, and trustworthy reasoning. These principles prevent overfitting, support adaptive learning, and ensure that AI systems remain both creative and reliable. As AI continues to evolve, equilibrium will become the foundational language for robust, ethically aligned intelligence. Despite the promise of CSE and CEC, challenges remain. Defining appropriate metrics, managing computational complexity, and ensuring ethical alignment require ongoing research. Future directions include hardware implementations, self-regulating agents, and integration with thermodynamic and quantum frameworks. As these challenges are addressed, equilibrium-driven AI will unlock new possibilities for adaptive, resilient, and ethically sound intelligence. Summary: embedding cosmological self-equilibrium and the cosmological equilibrium constant in AI design marks a major step toward robust, adaptive, and ethically aligned intelligence. Rather than relying solely on scale and data, equilibrium emerges as the foundation for next-generation AI. By balancing creativity and structure, exploration, and integration, these principles guide AI toward a future where intelligence is not just powerful, but also harmonious and trustworthy. As we look ahead, the integration of cosmic balance into artificial intelligence offers a new paradigm for machine learning and AGI. By embracing equilibrium, we can build systems that are not only smarter, but also more resilient, adaptive, and aligned with human values. The journey toward equilibrium-driven AI has just begun, and its potential to transform technology and society is truly cosmic in scale.